Group 1 Trebuchet Project. A trebuchet is a war machine used in medieval time period to hurl large stones or rocks at the enemy. Task at hand. Our task was to design and build a trebuchet within the given parameters and restrictions. Parameters and restrictions. Instead of launching large stones, we were instructed to launch a marble instead. Our only source of power could be the counterweight or counterweights that our group decided upon. All of our materials had to be approved by Mr. McHugh. Our trebuchet could be detachable, but all the parts had to fit inside of a 1 foot by 1 foot by 1 foot box. Our design had to be built from scratch. And lastly, at least 25% of it had to be laser cut or 3D printed. Our goal. The entire goal of this project was to make the most efficient trebuchet according to the efficiency equation given to us. To have the most efficient trebuchet possible, we would have to maximize our range and use the least amount of counterweight possible.
So now we move on to the design phase. So as Peyton said, the goal was to maximize efficiency according to the formula seen here. Well, what does that actually mean? Well, in short, the goal was to transfer as much gravitational potential energy from the counterweight into the range of the marble. So first, the gravitational potential energy gets transferred to kinetic energy, and if you have a really good launch angle, that a lot of that kinetic energy will get transferred into range. So there's kind of a two-part process to maximize this efficiency. And our formula is kind of a blend of the energy efficiency and range efficiency on the simulation. So we decided that both of those are very important. And so therefore we had adjusted the different parts of the simulation to maximize both aspects. I would also like to point out that our range efficiency was 1.014, which is somehow better than possible. So that was kind of interesting. We also, some important results, some findings from the simulation. We decided to use a 4-to-1 arm ratio, which means that the long arm is 4 times as long as the short arm. We found that was the ratio to use to maximize both efficiencies. Also, we used a very small weight, only about 350 grams. That equates to about 3/4 of a pound. Again, it's not going to go very far. It's not very exciting, but we're going for efficiency, not range. And so here's some pictures of our initial design. We decided to have triangular sides. They'd be simple to construct. We just 3D print them, and they'd also provide some stability. And we decided to laser cut the bottom panel, and originally we would just have the marble slide along that bottom panel, but as we'll talk about later, we decided to adjust that later in the process. We had a balsa crossbar that you can kind of see in the picture on the right, and we just used that to add stability and keep the two side triangles from trying to warp together or bend or shift in any way. We also used a eye hook and tack release mechanism as seen on the picture on the left. That allowed us by bending the tack back and forth, that allows us to easily adjust the release angle. And so that's kind of the majority of the major design decisions in the design process.
What went well? What went well for us was that our measurements were pretty accurate and precise. Our parts were aligned very well with each other and basically perfect. Our materials were easy to use and to construct. Our and our building process was fast, efficient, and had no major problems. The process. Our first step was to use a 3D printer to make the vertical section of our base. This ended up holding up very well. Next, we hot glued the 3D printed parts to a wooden base. The arm was the next to be built. The arm in total was 12 inches, the long arm was 9.5 inches, and the short arm was 2.5 inches. This was possibly the simplest part of our construction process. We then added an aluminum rod over the previous projects as our pivot. The rod was placed on the arm and attached with hot glue. The pouch for the counterweight was the next piece to be added. We took a piece of cloth and folded it to where it held 350 grams efficiently. We then braided fish line to connect the arm of the pouch. We believe that this fish line would have a stronger hold and wouldn't have any slack. The sling was the final piece we put on. We created a small pouch that would hold a marble so it would fly out easily at our projectile. We then used fishing line to connect the pouch to the arm, which we put a little loop which would come off with a nail at the end, and then we glued it to an eye screw on the other side. And after that, it was basically done. Our design problems. Our first 3D printing experience, we were making something too big, so it decided to warp on us, and how we fixed that is we started putting little circles around the outside of it so it would, protect from warping. And we actually added a support beam on top, or on the front of the 3D base, so it would give us a little more support, and the base wouldn't go side to side. It basically did up well. And this is our final product. As you can see, where we used the 3D printed, we printed them in halves, so then we had to glue them together. In the right bottom, you can see the support going from the 3D base to the 3D base. Up at the top, you can see our aluminum rod holding the arm, which you can see the short side and the long side. The braided fishing line holding the pouch. And then you can see the little pouch that held the marble, where we glued it to the eye screw, and then you can, if you look closely, you can see the loop that is around the screw, which would then allow the string to come off and throw our projectile, which was the marble. But underneath, we have a little guide track that we thought basically helped the marble stay on that straight line as it was moved by the dropping of the mass.
In terms of the performance, it's pretty simple. It's pretty much like every other trebuchet. You just pull it back and let it fly. What worked well, the fishing line I think worked pretty well. The 3D printing, we had some issues with it warping, but once we got that worked out, it worked well, and using less weight obviously due to the efficiency. What we could have done better, possibly oil on the straws at the very top, cut down on some friction, and maybe a better pouch for aerodynamics. As for the results, we finished with 79% actual efficiency while we simulated 100%. We didn't expect to get 100%. That's almost impossible to do in person, but we got it 6 feet, which is pretty close to what we wanted.